The title of my talk today is What's Missing for Robotics-first Foundation Models. And to preface this, I think I really want to emphasize the absolute amount of energy right now that's happening in embodied AI and robotics specifically. Even today at CVPR, I see so many times roboticists, which this is their first CVPR. I think it's the general trend of a lot of converging trends in different fields from language modeling and computer vision and embodied decision making. So I think it's really such an exciting time right now to be working on these problems. But the purpose of my talk today is to really try to paint a picture of what I view as the bleeding edge of modern trends that are ongoing in robotics, and more importantly, ask some provocative questions about how understanding this bleeding edge can point us to the missing pieces and open challenges that are on the path between us and really solving general purpose robotics. The work here that I'll discuss today comes from a great group at Google DeepMind, and the controversial opinions are only my own, especially the wrong ones. To give a brief glance then at today's agenda, I'll first motivate what is a robot foundation model, and I think you've heard today from so many great speakers, so I'll keep this brief. But most importantly, I'd like to focus on a few missing pieces that I hope will paint a path for what are the most important problems to solve before robotics become generally accessible. And finally, I'll save some time for the horizons of how the field might evolve at a meta level. First off, some very brief preliminaries. The modern sense plan act paradigm in robotics as such is a pipeline system, right? You have perception, understanding the world, you have planning, how you synthesize different types of information, especially semantics, human intent, etc. And of course, control and actuation, moving robot to influence the world. And what this has looked like in the modern era, and I use this to broadly, the loosest sense in the last 10 years, is that robotics has been very interdisciplinary, a very full stack effort where advances in perception, in language, and other domains are quickly adopted and utilized by roboticists to drive progress forward. This usually looks like taking the state-of-the-art bleeding edge model from CVPR, plugging that in as a perception stack, taking some kind of off-the-shelf great planning system, either symbolic or recently a learned system, and then really focusing on the control part is the last mile. And this has worked pretty well, I think, especially when we were working with like scaling up CNNs or scaling up initial smaller scale planners. But in the age of foundation models, I think some of the lessons that we've really taken to heart as robotics people in the last 10 years may not continue in the next few years. One issue you might think of is that it's great to keep taking these off-the-shelf state-of-the-art models, but of course these are frozen, they're pre-trained, they're not optimized for control, they're not optimized for decision-making. And the same for the language model planners, which again, these days, if you really view emergence as a phenomenon that only exists at scale organically, well, maybe the types of emergent capabilities, intelligence you need for low-level control are not the same ones that you need for internet-scale text modeling. And of course, the second part, which is related to that point, is that the bottlenecks between these modules are very narrow. They're very they're heuristic driven, they're expert defined, and they're not expressive enough perhaps to encompass the benefits of scale and transfer that we all know and love from foundation modeling. And so how do we tackle these two issues then? Well, maybe we could take some lessons from trends and practices that have worked in foundation modeling. I'm sure all of you guys know this story, but from language modeling and from vision, there's all these separate tasks and data sets and specialties. And the insight of scaling large-scale, internet-scale foundation models is that by treating these problems all as interoperable or homomorphic, is that by breaking down the barriers between the strict definitions of what you call sentiment classification versus what you call summarization, you get a lot of benefits and really great scaling trends. And then in robotics, right, going back to the modern sense plan feedback loop, where we today still have these very big brick walls between these modules. Is there a way we can break them down? And if we can do so, that would be a robotics-first foundation model. And again, I think we have some ideas of how to do this, and I'll talk about that in today's talk. But I think even beyond that, there's a lot of questions that we don't yet have answers to, which I think will be very exciting to make progress. So why do we even want to do this? Okay, let's say we break down these brick walls, we have a robotics-first foundation model. What does that mean? I think there's three missing pieces that are really nice properties that we see in today's language models and vision language models that we, as of today, do not yet see in robotics. One is really positive transfer at immense scales, where you basically can assume by default that positive transfer and scaling will work, as opposed to in robotics. These days, it's more rare than that you see positive transfer in cases where you get negative results. And again, when this happens, you can start making predictive scaling laws about how much you should scale, how much compute, how many tokens you need, and robotics is far from that today. Another one I think that is very close to my heart is steerability and comfortability, right? In my opinion, this is what really made me see the light between GPT-2 and GPT-3 eras, where you saw that few-shot learning, where you saw prompt engineering really start to take off at a massive scale. And in robotics, I think we're far from that. And finally, I think scalable evaluation is an aspect where I really enjoy the progress that's been made in foundation modeling, with everything from very realistic, meaningful evaluations to predictive benchmarks that correlate well with how users actually would leverage the capabilities seen in these models. And my claim here is that these properties are not just nice to have, but we actually need them in order to tackle the full unstructured wilderness of the real world. Again, robotics has kind of sped run the scale up from one bin for indiscriminate object picking to one room to one lab building, but to go from here to all the VC-funded humanoid companies and home robot companies and assisting the elderly and playing with your dogs and kids, this is kind of a huge gap, I think, that you don't get by just incremental progress, but by fundamentally transformative paradigm shifts, which can leverage emergence scale generalization. And the hot take here is that I think while we see signs of life today, I think if you froze technology today, you cannot solve robotics. And again, I think there's companies and startups and academics betting on this, but it's just a data problem, it's just engineering. I think there are still fundamental paradigm shifts that are algorithmic or maybe data breakthroughs that are needed until it's going to be tractable to try to go and solve robotics. And let's then jump into the nitty-gritty of these missing pieces then, right? So the first one I mentioned was positive transfer from scaling. And I think, to kind of illustrate what this means, I think we can just point at all of the kind of forerunners in language modeling and VLMs, right? You see these great large-scale internet-scale data sets. You see great, scaling laws and chinchilla optimality. And again, I think this is building off of the fact that passively scraping the internet gets you a lot of great properties that are good for language modeling and vision language modeling. But in robotics, that's not the case, right? So I think in robotics, in order to study how you can get positive transfer, you need to first scale the data. And there's probably two ways, which I'll dive into shortly, is one, maybe you can just make robot data look more like internet data. You can just treat them as the same data source. And the second is maybe your specific robot, there's not enough data, and even with $1 bajillion, you can't get enough. But maybe if you pull together all of the robot data that's been collected across different embodiments, tasks, environments, maybe you have a better shot of seeing some kind of positive transfer and scaling loss. So again, vision language models. This is kind of the golden standard for what we want to model the properties we'd like to see in robotics off of. This is one existence proof of concept of what's worked. And VLMs capture both visual and semantic knowledge of the world. And then you put it side by side here. This is the rough network architecture for a model called RT1 from our team from almost 2.5 years ago, which is kind of like a homebrew garage band transformer model that has these components of a perception vision encoder, some kind of like a cross-modal attention, which we use SOM for, and then transformer blocks to do the bulk of the reasoning, and finally some kind of action token output. Again, these are design choices that were really optimized at our scale on our problems, which were still pretty large scales by academic domains on hundreds and hundreds of robot tasks. But again, if you kind of squint at this, these components start to look like the design decisions that are used in state-of-the-art vision language models, right? And you can kind of just like try to think about how you would fit the kind of design choices we have to make at the small RT1 scale into a large VLM, and you see a lot of properties that are the same. Again, these are discretized tokens. They're very similar, just maybe with some slight output differences and input differences. But maybe you can just use the VLM as a policy. You don't need to iterate at small scales on your homebrew garage band policies. You can just leverage the kind of great work and infra and data from vision language model. And then the main question becomes, well, how do you align the action domain? How do you align the action manifold? And again, this is what our actions look like. They're kind of robot specific, but they encompass things like positional change and rotations and gripper open close and terminate action types. But that's broadly, going to be specific to a robot. And you can choose to discretize them. But I think the main point is that these look still a little bit different, right? From like the text you find on Wikipedia articles or on image captions on the web. But maybe there's ways you can just make them the same by just turning it into a string, the most naive thing you can do, and see how that works. And that's exactly what we did in this work called RT2. We just converted the tokenized, discretized robot actions into a string, such as this list of 8 integers, and you can just treat that as a caption. So robot action prediction is now just a V2A text. Of course, there's alternatives and that we can think of, such as maybe we use floats, but then there's more tokens and inference latency is a thing. You can use extra IDs or like least use action tokenization. You can use strings, and I think these are all very compelling choices. But I think the most simple thing to start with is just turning your raw robot actions and just casting it as a string and seeing what happens. And this is what's now called a vision language action model that treats actions as just another modality represented in text. For the backbones, we looked at PolyX models, which is a vision language model from Google, as well as PaLMi at the 5B, 12B, and 55B variants. And importantly, we co-fine-tune it. We co-train the robot data at the bottom along with the original V2A data, the internet data that the original VLMs were trained with to start. The robot data is this offline data set that we iterated on for RT1 and many other works. It's a large expert demonstration data set that we've saved offline. And what we see then is that when we train this large VLA model, we start to see some emergent skills. And I use emergent in the sense that these were not specific capabilities, such as OCR or recognizing flags. These are not any concepts that we collected data for in our robot data set, but kind of emerged via positive transfer from whatever semantic concepts were present in the internet scale VLM training, the VLM data. And quantitatively, right, post hoc, we can kind of try to squint and see what kind of these new capabilities are, and we roughly group them into things like symbol understanding, reasoning, or human recognition. And we see that this is indeed positive transfer happening thanks to the VLA paradigm. And again, though, those were kind of like canned evals, right? You don't necessarily care about if you're a roboticist, whether or not your robot foundation model recognizes Taylor Swift. Maybe you do care about, though, is generalization to distribution shifts like lighting conditions or new objects or new background conditions. And here we see that actually the VLA models, the web social data, also gives you some of this for free just by treating robotics as the same as internet data. Switching to the second part, though. So we've treated robot data now the same as internet data, but oftentimes maybe that robot data still isn't enough. Would you get any additional bang for your buck by training on all the robot data, even if the robots look different than the one you have in your lab, in your factory? Here we had a cross-institutional collaboration called Open Cross Embodiment, where we pulled together the data sets that were open source from more than 30 robot labs and aggregated together and see whether or not we could get some nice scaling properties by treating all the robot data as the same. And this data set is very, very heterogeneous. We have many different robot morphologies and embodiments. We have many different environments across the world and many different semantic tasks that each of the individual researchers I care about when they collected their original data set. It's different from clock folding to this like cable routing where you have to put a cable very dexterously into this small socket. It's really quite diverse. And with this diverse data set, we studied kind of the scaling properties as 2 model classes. One is the RT1, the small homemade transformer that we had 35 million parameters, as well as RT2, the full VLA 55 billion parameter VLA scale, to see whether or not treating these different robot action data sets as just input is some robot images, output are some robot actions represented as strings, what would happen in this case? And here, surprisingly, we actually see signs where the generalist policies, which are trained on all of the robot data, outperforms the specialists, which are optimized for each of their evaluation settings. And in this case, right, it's actually, I think this was to me very shocking because for each of these individual kind of labs here, each of these logos corresponds to a lab. There, generally, I think the best accepted, understanding of robotics is that if you care about maximizing performance on your specific task, on your robot and your setting, like you should just train on robot data from your robot, because adding any other data is going to be, not as, it's just going to your policies will not be robust to those. They're going to overfit to them. It's not going to help. But in this case, it seems that training on all the data actually improved performance, even if you only cared about performance on your specific setup. That was pretty, exciting to see in robotics, because this is a trend we've seen in other fields, but in robotics is really, really rare so far. And again, the improvement gain was almost 50%. Another interesting trend that we found is that actually we were getting to the point where we were seeing that smaller models would underfit this large heterogeneous robot data set. And again, overfitting is normally not something I think that underfitting is not something that we usually see in robotics, because usually the data amount is so small that model capacity is never an issue. And here it was very surprising that model capacity actually was required to kind of soak up all of this diverse robot data. And one big question though was that, great, you had all this robot data from all the robots, was it even needed? You already had all the web data from RT2. Does adding all this incremental, process alignment data add anything at all? And the good news is that we did find there was, a lot of these spatial reasoning skills about the motions and the precision of specific tasks, like whether you put the apple on the clock versus near the clock. These were tasks that only adding the robot data would enable the policies to do, whereas the internet data alone wouldn't give you these understanding capabilities for free. As a brief recap then, we've seen attempts at data scaling and positive transfer in two projects that I just highlighted. One was taking our robot data set from RT1, putting it alongside internet data and treating them the same. And then we scaled it up even further by taking all the robot data from many different embodiments. And we saw that in both cases, by treating robot actions and robot embodiments as just another data modality, you did see signs of positive transfer. And again, for RT1, this was great. We do well on the train set and in distribution. For RT2, this was we start to get internet scale semantics. And for RTX, we start to understand spatial precision and concepts like that, which are important for action and for physics. But I think that's where we got to maybe end of last year, I would say, the state of the world. And since then, though, I think there's many open challenges and things which do not work that I want to highlight. One is that VLAs in current training paradigms still overfit to robotics data distributions. What I mean by this is that we take a VLA, we kind of query it on VQA tasks like an internet image prompt, internet prompt, and it does well. We give it a robot image, ask it for actions, it does well. When you try to mix and match across these data distributions for both the visual latent space as well as for the text input space, it doesn't really seem like you're getting a ton of transfer. And this is a very, interesting failure mode, because it suggests that, there are still fundamental issues with how we're doing code training, how we're mixing robot data with internet data. We also see that reasoning, right? We oftentimes see that reasoning stems from the power of language model backbones from language model pre-training. And it seems that how you can mix this kind of reasoning process with low-level, physical action reasoning, that's also not, going exactly as expected, because we see cases where, for example, here, your reasoning and planning works well when all the objects are out of distribution, but when you add one in distribution object, such as a cocan, your model starts to revert to what it knows and just immediately, even though it can kind of knows, hey, if I want to hammer a nail, I should use the rock. It's never picked up a rock before, but it's picked up tens of thousands of cocans. So even though it kind of reasons that it should use a rock, it still goes for the cocan. Examples like this are just, they're everywhere, but I think they're not as normally as visible. So I just wanted to highlight this as interesting failure modes. And finally, right, how we actually, the model architecture decision, the design decisions are also not well thought through. Recently, there's a paper actually just from 3 days ago studying how you tokenize and how you represent your action, continuous, discrete, classification, what actual token choices do you use, that I think is a great step in the right direction at making, VLA training more of a science and less of an art. And moving on then, let me just check I'm doing on time. Okay, great. So the next missing piece then is steerability and promptability. I think this is very interesting because in robotics today, oftentimes we kind of historically, due to the scale of the robot policies we've been working with, we've really tried to constrain the amount of entropy and information that can be fed into the policy's input, right? Usually it's just one image, or maybe you frame stack some history of the past images you've seen, and then you convey a goal in the simplest way possible, right? A one-hot ID, a very simple, English sentence, or maybe a goal image. But generally, you're not really expanding the throughput of the bandwidth of your information input to the scale of like an open-ended chat interface as many language models see today. And again, I think we've seen in language modeling how large context windows enable so many great emergent capabilities, such as two-shot learning, such as, really being able to hone down and do chain of thought reasoning and or reflection, all this kind of good stuff that we can't really have in robotics because our input domains, interfaces are just so constrained. And I really want a promptable robot, which you can just say, hey, can you try again? Can you move too far right? Can you just adjust it on your next try? We don't have any meta learning like that right now, and it won't naturally emerge by just adding, more of the same types of robot data and more of the same types of internet data. There has to be a paradigm shift in order to get from us, where we are today, to a promptable, steerable robot control model. And here I think, maybe one hypothesis here is that maybe it's language that's the bottleneck, at least language the way we approach it today, right? We've been kind of taking all of the recipes that have worked in other domains and we've tried to say, okay, let's just add language as a conditioning modality for robots. Let's just add language data sets. But this maybe misses a lot of what makes robots hard, right? What makes robots different and unique and an interesting problem to study are the motions, the physics, the causal nature of interaction with the world. And when you try to condense everything into something that, a language model Wikipedia article might look like, maybe you just lose a lot of that in translation. And so towards that, maybe honing in on the motion of robotics is what this work tries to do, called RT trajectory, which takes the idea of hindsight experience replay. You take the goal image, you turn that into the target for your policy learning, but does that for the motion of the trajectory that was executed. When we collect robot data, oftentimes the end effector, or proprioception for all of your joint states and your motors are kind of stored, and we currently just toss all that away when we just save out RGB action trajectories. Maybe you can actually utilize, the motion of what happened in the real world and use that to condition your policy, because you already have this data for free. We just currently toss it out. So what we do in this work is we take that proprioception and effector data, we project it into 2D RGB space, and that just becomes a kind of visual hint, a visual chain of thought, if you will, of not just what you should do. You should, put the chip bag in the drawer, but how you should do it, how you should approach it, from what angle, where you should close, how you should avoid obstacles, at what depth and what heights you should be operating at. And then we feed it into an RT1 policy. And what's nice is that even though training this was automated, at inference time, then maybe getting this trajectory from scratch would have been hard, but the policy is agnostic to what trajectory you give it. It doesn't have to be hindsight. It can be hand drawn by a human. It can be you can take a human video and do pose extraction with the hand and then get this trajectory out of there. Or you can even give foundation models, either generative image models or language models, to go and predict what the trajectory should be, and then that can condition your pre-trained policy, which is only trained on hindsight trajectories. And what's nice here is that we start to see signs of motion generalization, right? This is where you have tasks which have fundamentally, maybe they're operating at different heights or different motions, just combinations of state action transition, which were just never in the training data, which has been traditionally hard for some of our policies, which were just kind of overfit to pick up the Coke can and that's all I know. And you can't really generalize to Coke cans and vastly different motion profiles. But we start to see that here with tasks such as swiveling chairs or folding towels or picking objects up from a chair at a very low height. But most interesting for the topic here is that this was the first project I worked on, at least, where I really got some kind of shadow or some hint of I felt that prompt engineering was possible. Here, we'd sometimes try out, evaluations in very different settings in like a home setting, like an IKEA-like setting with dark wood furniture at different heights. And the robot would sometimes fail to generalize these out of distribution settings. But then just by drawing a prompt trajectory differently, the human can kind of learn the failure modes, the eccentricities of the robot, and just by like, a trained operator could then learn to draw better trajectories and then start to zero shot new tasks. Again, this was no other policy that we have today where the input is always something as simple as, hey, pick up a Coke can, pick up a Pepsi can, close the drawer. Going from that to like, hey, you're in this brand new setting, the drawer is going to be 5 centimeters lower than you're used to, and there's also clutter. Can you go and do that? Like, there's no way any policy could be responsive to that. Yet with trajectories, it seems like sometimes we would get that. And concurrently, it's been really great to see over the past 6 months, a lot of other works also kind of adopt similar paradigms using, point tracking, optical flow, using other kinds of motion representations to also have, touching upon the same idea is that what makes robotics unique is physics, is motion, is trajectories. Maybe adding this information to our foundation models can unlock things which language cannot. Which is very excited to see, but I think overall it's still very nascent, and none of these methods have been scaled up to the level of, let's say, a 55 billion parameter vision language action model. Next up, though, one other interesting question I was asking, maybe a year ago was, I have all these rights with language. In the section of this section, right, was like, what can we do beyond language? But maybe language was not the problem, just the way we were using language, that we're using language in too simple of a way. And if the language was more grounded in motions and physics and what makes robotics unique, if it would be more hierarchical and granular, we could get the benefits. And so in this project called Archie-Hierarchy, we would kind of do a chain of thought prediction where you turn the pick cocan, the very abstract, very like long horizon task, into intermediate, very grounded language motions, like move your arm right and rotate it clockwise and then close your gripper, into like language that's very grounded towards very short horizon actions. And again, this can kind of be viewed as like chain of thought, still using language as the chain of thought medium, but doing it in a way which is much easier than perhaps to generalize. And what's interesting then is that this unlocked learning from a category of tasks we had been collecting for over 6 months that no other policy was able to use that data from because they were just so hard. So it's kind of like tasks related to the serial task where there's like a small gap, you have to put a bowl and you have to push a lever, and then there's this like cluttered thing of oatmeal packets and it's like a slightly more dexterous and precise than the tasks we'd seen before, but policies were just really struggling to kind of work at the entropy of these systems, which was just a little bit more complex than before. And then these language motions are what unlocked the ability to work on those types of tasks. And talking about like pumpability and steerability, we also saw that having interventions in language of, hey, actually, you're doing the right level control. It was just your intermediate plan of translating closed the pistachio jar. You wanted to move up when you should have moved left. Humans could correct this in a dagger-like setting in a much more efficient manner than it would have taken for low-level action interventions. And this was a way to kind of scale up this chain of thought level improvement where you don't always need to make your, iterate at the action level, which is the most expensive level. Maybe sometimes you can, intervene at the language motion or hierarchical planning level. That was also kind of steerability and probability that one of the rare instances that I saw. And to kind of summarize here, RT1 and RT2, even though they were scaled up so much, they were still shoving together all of the foundation model knowledge, all the large data sets through a very narrow bottleneck of simple language instructions. And by widening that kind of bottleneck via either things like time-centered trajectories, via motion-centric representations, or even via language, just better language, seem to unlock more of the intelligence that's contained in these internet-scale foundations. And the question here becomes is that I view these projects kind of as proof of concepts. I'm very excited about the results, but again, we haven't scaled them up yet to the full internet scale. And the question is maybe to scale them up to, a full vision language action model, maybe we need more robot data. And my hot take here is that actually this is not a call to action for me to, a lot of, companies, for example, right now are convinced that algorithms are solved, it's just data, and maybe this slide would have suggested that, but I think we don't actually know what kinds of robot data you need. And so if you prematurely try to scale, deploy robot and you're correcting or not correct, maybe sometimes that wouldn't have been a recoverable mistake. So again, I don't think I'm suggesting to not do that, because I think we definitely need to do that, but I think there's also work that robot researchers need to think about on, can we figure out the right types of modalities and data sets and tasks and skills and labels that we need when we go about collecting these like society scale data sets. And finally, then I think one missing piece is scalable evaluation, right? This is, I think, generally a problem throughout all of AI right now. We see that all of these different, benchmarks and, leaderboards are oftentimes a lot of hype these days because they're very easily gameable. But they're good attempts, I think, at least in foundation modeling broadly, to try to capture various representations of capabilities that we want. And the challenge here, however, is that all AI models across the, broadly the field everything wants to be a generalist these days, right? And that's a very high claim. If your generalist model can do everything, how do you back up rigorously that you can actually do everything and be robust at that? And I think this is clearly already an issue in foundation modeling, but I think things like these ELO-based leaderboards or just getting these models out and deployed in open source or even as close, source APIs, these are ways where you can just leave it up to, the court of the public to kind of say, hey, are your models actually good? And in robotics, this is kind of hard, right? Because robotics target physical data distributions, and it's not really clear whether or not some representative small set of evaluations can capture all of the properties you want to measure, or if there's just a lot of stuff that you need to do before you get to a product that's out. But I think regardless of what the answer is, the problem is very clear. And the problem is that as our policies within our team at Google DeepMind have scaled, the amount of evaluations we've had to do have also scaled, right? And I think this might not sound like a lot, 3,000 or 6,000 trials, but if you consider that each trial can take up to 10, 15 minutes, this is quickly going to become intractable if we add another order of magnitude to what we claim our policies can do the next year or two. That's just not going to be tractable for any industry or academic lab. Maybe one way is we can decompose the kind of attack space of the claims you want to make about these robot foundation models and break them down into particular axes that are meant to represent policy generalization that encompass properties that we hope to measure, such as maybe different backgrounds or adding distractor objects and clutter or changing lighting conditions, adding new objects, etc. And maybe we can measure generalization gaps from our training set to our test set. We did this in the real world, and we indeed found that maybe some of these like axes of generalization, these factors of distribution shifts, were harder than others, and would have these kind of scaling curves as you kind of added more of these to your training. But I think this was kind of just an initial kind of attempt at codifying or formalizing what it means for your robot foundation model to be a generalist foundation model. And it's definitely a challenge now because every new foundation model robot policy that comes out kind of has to do all this on their own again and define their own evals and define their own benchmarks, and it's just kind of hard to compare apples to apples in today's academic landscape. Maybe another path, however, is of course using simulation. And today there are so many great talks on world models in sim, especially for AV and in robot manipulation. It's been a bit harder because manipulation, right, with contact forces and physics and visual distribution shifts, and oftentimes data sets are very tuned to one limited setting, which raises the bar for how realistic the sims have to be. This has been an ongoing challenge. So an insight in our recent work here called Simpler was that maybe you don't need a full fidelity digital twin in order that you would need for sim3 training. Maybe all you need to do is optimize for correlation between the ranking of policies in sim and how they would rank in the real world if you had evaluated them in the real world. And by doing this, we would try to just get a minimal viable sim that gets you a useful signal of which checkpoints you should use, which with kind of policies you should devote your very expensive real world evals to. And again, I don't think it's perfect, but I think it was working well for various classes of generalist robot policies that we were operating on, such as RT1, RT1X, RT2, etc. And maybe, again, a shout out to concurrent work or kind of related works, right? I'm the PRISM one related today from Alex, Unisim from Sherry, also Genie, which is a latent action condition video diffusion model from Google, DeepMind. These are all kind of, I think, directionally where we would want to go for seeing if these kinds of approaches can also act as good offline policy evaluation. And my hot take here then is that I think despite all of these great progresses, I think real world evals will always be the gold standard. You can never replace that. I think these evals, offline evals can help you decide which, how to spend your limited bandwidth for real world evals, but it won't replace them completely, right? And then so if you actually need real world evals and you need them at scale, that becomes a very challenging problem, right? And it's perhaps one that will be solved by products deployed in the wild where you actually get scale eval from actual user deployments, like people actually using your robots and your robot policies. And finally here, I'd like to talk a bit about maybe what this means for what we can think about for how we can predict the next year or 2 years of what my robot foundation model might look like. And the first one here is a recap. We talked about positive transfer and the scaling laws of robotics as we increase our data sets and our model capacities. The leading edge here from what I talked about today, I view them as the vision, language, action modeling paradigm, and a lot of improvements in process embodiment training on many different types of robot data. Here, this is my grade, again, just my own opinion. I would give the field a 6 out of 10. Is it how much we progressed and how much remaining kind of unknown unknowns we have. I think, as you saw, the failure modes, we're still overfitting. It's still, BLA training is still more of an art than a science of your data training mixtures of how you go about doing that, your action tokenization of decisions. And I think there's a lot of science that still needs to happen here. For steerability and promptability, again, here we talk about going beyond language. Let's think about motions, let's think about trajectories. Here, I would say the field's at a 4 out of 10, because I think while we've had signs of life, maybe sparks of what could become a promptable or steerable robot learning paradigm, none of these have been scaled up to a large scale. And we don't yet know what kind of data requirements or kind of bottlenecks that will occur when we do try to scale these methods. And we don't know if these will scale to more dexterous embodiments such as humanoids or consumer robots. And finally, for scalable eval, again, maybe we can think about generalization or simulation. I would score this at a 3 out of 10, just because we oftentimes don't even know what we should be evaluating for, right? Even before we can design the eval, we need to kind of set up the paradigms, the structure, the formalisms, all of that is still kind of very ad hoc, and it's done on a per project basis almost. And so definitely in the future, I hope that maybe either concerted efforts or just, by bringing robot action prediction and low-level control closer to foundation modeling, these problems of evaluation can also become more homogeneous. With that, then I'll take these final, last points that we just saw, like why I gave these ratings. Maybe we can try to predict what solutions to these might be. This is, I would say, what might happen in the 2025 to 2026 horizon. I think the first one is that, once we understand BLAs better, once it turns into a science and it's not just an art, I think maybe robotics research will also start to split into pre-training and post-training, just as foundation modeling has. Once you have access to very robust starting points of foundation models from, maybe from Google DeepMind, maybe from OpenAI, from other companies. Once you have great starting points, then post-training your robot will become more of what your daily cycles are going to be looking like as a practitioner or as a researcher. For robot-specific data, again, I think robot data engines, again, if you're really thinking about scale deployments at a society scale, here I think is where industry and startups will be able to contribute a lot to the field. And what that's going to look like, we'll see. But I think the race is really starting up this year with so many startups and exciting new companies being formed. And then finally, for evaluations, with all of the amazing progress we're seeing in video modeling, again, I think I'm really excited to see what the action condition variant of these world models will look like. How well they'll be able to model out of distribution behaviors and not just in distribution training data. Because I think for evaluating robot policy, you don't just want them to be aesthetic or realistic. You want them to actually measure these long tail of very rare events, or you want them to model contact forces and physical causality, which may not always correlate to aesthetic pre-training video YouTube data that they maybe were trained on. As well as, of course, product deployments. So I think their evaluations is another setting where we'll see industry and startups contribute to. Those are, again, just my own opinions, but I think I'm very excited to see how the field of robotics research evolves. With that said, thanks for your time. Reach me on the email here, and I'll share the slides after, but thanks for your time.
Very much, Ted, for the great talk. There's already a question. You go ahead.
You mentioned some of the evaluations on the product, something like that, something like large number of participants, or maybe a company has a certain. So how would we go about knowing what kind of maybe actually we plan on doing so much, but actually the model performance. Like certain companies maybe using a certain range of power picture demonstration. Is there any scientific report on that?
So I guess the question here was, with texture randomization being kind of one axis of generalization, a distribution shift that seemed challenging, are there maybe methods or is there any data points we have on how to address that? I think it's also, there have been some works on like data augmentation for robotics, maybe in a semantic fashion, where instead of just like, broadly domain randomizing, like just random textures, actually using semantically relevant textures of like what's actually appropriate. Like you don't want like a, neon random RGB wallpaper in your home. You want wallpapers that are actually seen in people's homes. I think this is still very nascent, but I think there's already been very good results of people like pushing up on these like generalization settings with methods like diffusion models for innate.
Other questions? Yes, please.
Yeah, I was wondering, are you saying video data, real data, simulation data, they're all contributing, or if you have to pick one, which one would you go for, or is there a transfer between, or it doesn't even matter? In your representation, like where you look at.
Yeah, absolutely. So the question, I guess, is video data, sim data, real data. How do we view? Are they all equal? Do they transfer? My sense is at least based on the last few years, again, real data is absolutely king. So if you offer me the same quantity of real data versus sim versus video, I'm picking real any day of the week. However, then, maybe at some point there will be diminishing returns, or maybe if you offer me 1,000 times more or 1,000,000 times more sim or video data compared to robot action data, then maybe the trade-off starts to become different. But in the past, I would say that's also not a very good predictive measure of what might happen in the future, because in the past, again, the robot kind of foundation model policy capacities were so small that if you could only kind of operate over the scale of, 100,000 trajectories, then you would, of course, just operate on 100,000 real trajectories. You never had the opportunity to be operating at the scale of an intranet scale VLN, where you did have the capacity to consume 1,000,000 times more sim or video data. And I think we have the opportunity to do that in the next, year or even now.
Yeah, there was a question here in the front.
Thanks for your presentation. You're talking also about what's missing from the robotics and the vision, the language, and everything. Physical sense, physical sensing. Probably like people born blind, they can language instructions and physical interaction, they can still learn the patients that
Yeah, great question. So the question here was, physical touch, right? Sensing. This is so important for humans. How about for robots? I think my sense here is that, I kind of put two columns of like what could make robots steerable or what's missing from foundation models that's unique to robots. I would definitely put sensing and other modalities in this here as well. The reason I think maybe it's a little bit farther off, or for me at least not a top priority, is that I think just grounding the idea of temporal motion into like putting that into visual language latent space, if that is already so hard, then adding a completely new modality like touch sensors, where you don't have a lot of data, where it is noisy, where it's so different from internet data, that's going to be even harder. So if we can't even add trajectories and motions, then adding sensing data might be even harder lift. So that's why, for me at least, my aim is to try to make some progress on hitting the motions, the physics, the trajectories first, and then sensing maybe, I think, hopefully that'll tell us how we should approach sensing as well.
In the interest of time, let's have two last questions. So I see two hands. You can start in front and then other questions.
The interface between the higher level module and the lower level module is what language.
Yeah, great question. So the question here is that in this RT hierarchy work, the interface between the high level planning and the low level control was this like low level language motion. And does it have to be language? And yeah, absolutely. I think there's many other kinds of representations you could use. For example, even these trajectories is one, right? Your high level plan could be like, hey, how do I swivel the chair? And then the interface is this like RGB like curve. But I think there's definitely a lot more. Language is just a natural one where you could hope to get a bit more transfer from like, chain of thought in non-embodied domains, but great point.
And the final question.
Yeah, so I have a question around generalization versus. I feel like, reasoning about the conflict rather than the internet scale data. We still see data as an integration part, within the data. What is your thought about any architectural pieces that are reference to have all the things without relying on backup files?
Yeah, so yeah, the question was, interpolation versus true out of distribution generalization reasoning. Maybe oftentimes when we claim we're generalizing the new objects or light conditions, it's actually just interpolating the data that we already saw. And definitely I think, I think here, right, when I define emergent, I try to embrace this by saying that emergent doesn't mean that it's not present in any of the training data and it's emerged magically. It's that it was in the data, but internet scale data is too much for us to codify. So it's just emerging, like we're finding out what was in the data basically, right? Like we're finding out what's in the data and now it's being projected into the robot action space and we're seeing what has successfully projected. So I think, again, I don't even know if we need necessarily to solve like true generalization in order for robotics to work well. I think if we're able to solve like just interpolation at scale, that's in a very like, predictable fashion, I think I would be already happy with that in terms of getting general purpose robots. I think, but beyond that for AGI, I know it's a loaded term, yes, probably.
Okay. Sorry. So let's send the speaker again.